Hi, today we're going to be talking about permutations. One thing that I want to just mention is that permutations arise naturally. Let's consider this example of how many ways we can make a 5-letter password, assuming no letters are repeated and for simplicity that all of the letters are lowercase. So there are 5 letters to this. There's a first letter. For the first letter, we have all 26 letters available to us. For the second letter, well, one of the 26 letters has been used, so there's 25. The counting principle says we multiply these two outcomes. Okay. We continue in this way for the third letter, or the third letter in our password, which will be one less, 24. Then the fourth will be 23, and the fifth will be 22. Okay, so I just want to remind us that a factorial, for example, 4 factorial is 4 times 3 times 2, all the way down to 1. So if we were to rewrite this, we could write this as 26 times 25 times 24 times 23 times 22. If this was 26 factorial, we'd go down to 21, multiply by 20, and we keep going all the way down to 1. Okay. Now, we don't have anything that is, for example, less than 22. So all of this stuff doesn't need to be there. We can remove all of that stuff by dividing by 21 times 20 times 2 times 1. And this works out to be 26 factorial divided by 26 minus 5 factorial. Okay. Notice 26 was the number of letters available to us. 5 was the number of digits that we needed to select. So in general, this is n permute k objects, which is equal to n factorial divided by n minus k factorial. Okay, and so that's our general formula. I also want to mention that for a permutation, order matters. Okay. So for example, the password A, B, C, D, E is different from B, A, C, D, E, the one where the first 2 letters are interchanged. Okay. So that's an important fact about permutations. Okay. So here I want to go over a slightly more confusing problem in which we have the outcomes of tossing 3 coins. They all landed heads, but the coins are colored. And the fact that we have the outcomes of the coins being heads, heads, heads is a distraction. This is asking about the colors of the coin, red, blue, green. So there are 3 colors that are distinct. And we can reorder the colors. For the first color, there are 3 possible ways of reordering it. For the second, there's 2. And for the third, there's 1. So there's 3 factorial ways of reordering these objects. Okay. Okay, now for this last example, I want to ask you, in how many ways can we select a president, a vice president, and a treasurer from a list of 9 unique individuals. So for the president, there are 9 options to select from. For the vice president, there's one less because one was selected as president, and for treasurer, there are 7. This is going to be 9 permute 3. 9 individuals, we are selecting 3 of them. Notice order matters because, for example, being president is different than being vice president or treasurer. Okay. Now, let's ask a question about probability. John is one of the 9 individuals in the list of 9. What is the probability John is the president, and if these positions are randomly selected? Okay. Now, first thing that I notice is the total number of outcomes, if they're randomly selected, is computed by part 1 above. So any one of the 9 could be president, so 9. Any one of the remaining 8 individuals could be VP, and then the same for treasurer. So in the denominator, the total number of outcomes is 9 times 8 times 7. Let's think about the number of ways John can be president. Okay, so for the position of president, vice president, and treasurer. Okay, so for the president needs to be John. So there's only one individual that can be president, and that for John to be president. For vice president, well, there are 9 individuals, but John's one of them, and he got assigned to be president. So there's 8 outcomes left. For the treasurer, well, John's president and one individual selected as VP, so there's 7. So this looks like it's 1 times 8 times 7, which is 1/9. And this makes sense, if the first position they're selecting is president and they're randomly selecting from a list of 9, it makes sense that John has a 1/9 probability. Thank you very much.